Yes. You
Okay.
can start.
Hi, everyone. So sorry about the technical difficulties, but I guess switched from using Chrome to using Safari, and it's working now. I'm Anders. Me and my collaborators work on bottom-up synthesis of recursive functional programs using Angelic Execution. I know I've got like an hour to present, and I think I've got about that much material, but like I'd say if you have any burning questions that would help your understanding, obviously just feel free to interrupt me. It's no worries. I can't see the chat, so if you press a chat, then I won't see it. So I guess hopefully someone can relay your message. I did this work as part of my postdoc at UT Austin. I did it with Adrian Trejo Nunez, Ana Brandel, Swarat Chaudhuri, and Ishal Dillig. First, what do I mean by recursive functional code? I just want to make sure we all have our understanding correct. By recursive, I mean that the function can call itself, and by functional, I mean that we don't have to think or worry about updates. So namely, by talking about functional code, it's kind of like a restriction on the general problem, essentially just because if we're worrying about statefulness, at the same time as this, it's just kind of too much. The state space, I think, gets a little too hard. The reasoning gets too difficult. And so we just said, you know what, we're just going to do a simple task now, and maybe we can worry about stateful code later. And what do I mean by recursive? Essentially, by recursive, I mean, I'm discussing how functional code can express complex patterns like loops. So this is why recursion is particularly important, is because in this kind of core calculus, it's how you can handle kind of unbounded computation. Things that, you know, just like how whiles and fors and all that kind of continue along for not a fixed amount of time, it potentially infinite. We have kind of the same type of restriction, or we have the same capabilities by talking about recursion. So by talking about recursion, it kind of makes the problem a lot more important. So I'm going to give a little example of delete or del to save space on the screen. I'm talking about deling 0 from 100. That would return 10 because it dels this first one, and it only removes the first occurrence. And if I del 1 from singleton 2, I just get singleton 2 because there's no 1 in that list. Generally, in these recursive programs, I express these lists as a linked list. So 1 points to 0, points to 0, points to nil. I'm going to have some built-in functions. So I'm going to have head, which will just extract that first element that's pointed to, and tail, which will extract the tail of the list. So that's how I kind of can extract the various components that make a full list. And I also have a concatenation operator. I'm using this little @ sign, which is often used for append, but here I'm going to use it for consing or prepending. And I'm probably going to use all those terms simultaneously, so sorry if it gets confusing. But basically, I'm consing 1 onto 0, 0, and I get 1, 0, 0. So this little @ sign kind of adds on this node to the front of the list. So here's an implementation of del. In this implementation, I have kind of some basic if analysis. So if I do if x is equal to the nil, then it just returns nil. Otherwise, if the head of the list is x, if it's what I'm looking for, oh, this should be if L is nil, sorry, then I return the tail of the list. So essentially, if I'm in this sort of situation where I have just 0, 0, and I'm deling 0 from it, I just return singleton 0. Otherwise, I make a recursive call, recursively delete the first occurrence from the tail, and then I add the head back on. So if you spend a little bit of time thinking, you can understand that in the case where maybe you don't have the element, it just traverses all the way down to the back of the list and then iteratively builds it back up. So I want to be able to do synthesis from this. And kind of the idea is that it would be really nice if instead of writing code, we could write specifications. And this comes from the idea that code is really, I guess, when this kind of comes from a philosophical idea that I and some others have, which is that if you have to write code and specification, because code is actually runnable and necessary, your code becomes the specification, and nobody really seems to write specifications except for on incredibly high assurance software. So if you're talking about like an average programmer, one who might be writing up Dell, they're probably not going to be willing to write some sort of formal spec. The idea is maybe if you kind of write the spec as writing the code, you can generate, that's a way of kind of building some form of a specification. But so let's say that I want to remove the first occurrence of an element. Unfortunately, this kind of specification is a little bit difficult. It's not easy to turn into some sort of specification besides just writing the code. So I'm going to over approximate it. So I'm going to say something like the output of deleting an element X from the list is the size of that's going to be less than or equal to the list. If I check out the output, then it'll just return the singleton or the empty list because this is kind of the simplest program that satisfies this, which is unfortunate. So maybe I can say, okay, well, that spec wasn't tight enough, so let me add something else. Maybe I'll add an input-output example. And after I add this, the output actually looks pretty good. I mean, if you look at this, besides the fact that I typoed and have an X there, everything looks right except for the fact that this is a 0 and this is a 1. But fortunately, we can kind of abstract that out. So one of the benefits of Burst is that you don't require only some sort of very specific form of specification. You can kind of abstract out this 1. So just say for all X, and then you get a little bit closer. This 1 has been turned into head of the list. And if I have 0, I can abstract that out by another universal and just get del y from xyy returns xy. And that's sufficient to actually figure out the full output. So there's a lot of work in the domain of recursive functional synthesis because it's kind of an important one. It's this interesting combination of pragmatic because there's not statefulness, and also pragmatic because recursion is important. And frankly, I think that there's an element of a lot of people tackling it because it's kind of interesting. I just think that by having recursion, you really do have some interesting, fun problems. The issue with a lot of these works is that they have very, maybe non-intuitive is the right way to put it, non-intuitive specifications. So for example, like Smith and Myth and Escher all require input-output examples as the only form of examples, which is great. There's nothing wrong with input-output examples. But some tasks require, I don't know, I looked at the Smith paper and it's like, there's one task that requires like 20 examples. And at that point, why would you be using the tool? 20 examples is insane. And on Myth and Escher, they also have this weird restriction called trace complete examples. I'm not going to go into the details of it, but essentially you can view this kind of work in Myth and Escher as being very, it's just complex, you know, it requires the user to actually understand this notion of trace complete examples, which talks about kind of, they must know kind of what program they have in mind because they must know what the recursive calls will be. And it's just a little bit funky. Synquit is a different approach. It uses logical specifications, which is great. It's very general. It's able to tackle more types of specs than just input-output examples, but it does also handle input-output examples, although with the restriction that they are kind of like the logical specification analog of trace complete. One of the main issues, though, is that it requires writing in these liquid types. And liquid types are really impressive. They're really strong. They're able to give very unique specifications where the synthesis is almost non-existent. You almost know exactly what program it is if you give a sufficiently tight specification. But writing them is really difficult. This doesn't kind of move the needle at all towards being able to do any sort of interactive synthesis or any sort of interactive design where you essentially in Synquit, you really have to have a very, very tight specification. And then it's very, very incredibly impressive on that. If you give a very tight specification, it can handle, I'd say, more synthesis tasks than anything else, but it is very dependent on the spec. What we want to do is we want to focus on something that can work for everyone. So it's going to be what we are calling, or in this talk, I'm calling arbitrary behavioral predicates, which is essentially a relational over approximation of the function I want to synthesize. But more specifically, it's a function from inputs out and outputs to bools. So you can view it as a relation over inputs and outputs. And the satisfaction of one of these predicates I write as f models phi, which means that for all x in the domain, if I run phi on x and f of x, then it should return true. So for a little example, let's say that phi is true. It's just a constant function true, takes in two outputs and always returns true. That means that every f will satisfy this. It's vacuous, automatically when you run x and f of x on anything, it'll return true. So that means every f satisfies phi. So and then you can give more and more restrictions. So let me give one example. Let's say I'm doing a specification on input and output, and I'm saying, okay, I will return the ref implementation on input should equal the output. So this is a much tighter specification than F. It's actually kind of like the most tight specification you can write that has a satisfying assignment that you can write in this form. Essentially, what this does is it expresses anything, all Fs that are accepted for this specification are semantically equivalent to ref input. So this is a way you can say, oh, generate me some new implementation of rempit. And what's nice is I notice I wrote this in kind of like a Java-like syntax, not the OCaml-like syntax I've been using in the past. That's because these predicates are very arbitrary. We want to mainly be able to not inspect the actual predicate. And by doing this, we allow the predicates to be written in any language. We allow, it basically handles arbitrarily many cases. Here's another one written in like OCaml syntax. And this is saying, or ML syntax, I guess. This is saying that the input and output lengths are true, but note you can write it in this form as well. And you can even write it as like a mathematical clause. So, hey, if the input is greater than 2, then the output must be greater than 2. So in this way, these specifications are black box. I do not want to be able to inspect them when performing synthesis. Because, and this is kind of a restriction that we put on ourselves essentially just to make it such that our tool is more general. I guess that's the main idea. It makes it so that we can't put on these funky logics that prior work did, and we have an eye towards some future work in this, but namely, this is kind of the restriction that we're working under is you're not going to be able to do some sort of like pattern matching on the spec. So this really drives our synthesis approach. Namely, there's top-down and there's bottom-up synthesis. And for some reasons I'm going to detail, we use bottom-up synthesis. But let's talk about top-down. In top-down synthesis, what you do is you build up this empty program where you kind of have this question mark, and then you iteratively fill in the program holes. So let's say I'm looking, I've got this lambda x dot question mark because it's something, this is the hole. And then you can build this and separate it into two new holes, question mark 1 and question mark 2, or you can fill that question mark in with a concrete x, or you can say it's negative some other question mark, and then you iteratively kind of expand these question marks. So in this one, this question mark 2 was expanded into another plus of question mark 2 and question mark 3, and you continue this until you eventually find a satisfying program. Now, synthesis is this type of general purpose synthesis is a doubly exponential search space. So it's very, very complex, I guess, what you're looking through, and it requires being careful. And part of this carefulness is, careful is the wrong term. It requires pruding. You need to have some sort of practical solution to the fact that you're navigating this exceedingly large search space. And so in the context of top-down, a very common method is with domain-specific reasoning. Namely, you kind of look at a specification and then you use that specification to prune out partial programs, these programs with holes that are hopelessly invalid, that could not have any satisfying assignment to the question mark. And so there's no need to continue searching down them because just by virtue of the partial program, it's bliss. So in this case, say maybe I have a specification of no negatives, and maybe in my language I had no, you can't negate a negation. So I can just prune out this lambda x dot question mark. Dot negative question mark immediately. And so that has a large impact on the search space because then I don't look at this program or any of the children of it. And what's nice is that really fast when this reasoning succeeds. This is something, top-down synthesizers can be blazing fast. But reasoning doesn't always succeed. And usually once that reasoning fails, it kind of defaults to a just raw enumeration, and it's very slow in such contexts. So you have a little bit of a balance where you have to think about, okay, I really want to be fast reasoning, or in certain situations where you have a very tight specification, you can do this really good reasoning to really build up your synthesis tree. And this is kind of what Synquid does. And so when you can do that reasoning, it's blazing fast. Contrast it to bottom up. Bottom up uses so you can see top down because I have the arrows going from the top down. Bottom up does the reverse. It starts out with full programs and then kind of combines them to get larger and larger ones. So let's say I've got the full program lambda x dot x and lambda x dot 0. I can combine the lambda x dot x with itself, so I get lambda x dot x plus x. I can combine the x with the 0 and get x plus 0. I can take this x and negate it. I get a negative x. Then I combine this x plus x with this x, and I get x plus x, yada, yada, yada. And what's nice is that bottom-up synthesizers generally don't use the same type of domain-specific reasoning using the specification. Rather, it just kind of does evaluation. And so what pruning in this context means is it prunes equivalent programs. So this prunes hopeless programs, this prunes equivalent programs. So namely, you can see lambda x dot x is equivalent to lambda x dot x plus 0. You can just say, well, this is the same as this. Let me just prune out x plus 0. And this is really useful for interactivity. Bottom-up synthesizers, because they build up this search space, if you give refined specifications, it can be helpful. Oh, and then another idea, just quickly to mention, is essentially what you're doing is you're not searching through the search space of all programs, but you're searching through the search space of all programs, modulo, or basically all equivalence classes of programs, where equivalence classes are semantic equivalents. Also, this is kind of a bit of a workhorse. It just keeps going steadily. It's very nice in that way that it's not. It doesn't have the same sort of either very fast or very slow. It's just kind of plods along. So there's been some works that combine these two, like Dryad Synth and Duet, and they show, oh, look, if you combine both of this, you get something better than either of them individually. But in the context of bottom-up synthesis, we're going to focus on that for Burst. So Burst, we built the first bottom-up synthesizer that can synthesize these recursive functional programs from arbitrary logical specs. It also is able to do so with a full completeness guarantee. And some of the novel notions that we have are angelic recursion, and we use an angelic synthesis method, which has been used, I guess, historically for program repair, actually. And even though Burst is more general than prior tools, it actually performs comparably to them, or actually sometimes better than prior work. So I'm just going to quickly go through a table of contents. I'm planning on, in this talk, giving some high-level ideas about our algorithm. Then I'm just going to give a little bit more details about the specifics, and then I'm going to get really nitty-gritty if we have time to give some of the really fun details. So yeah, essentially what we're doing is we're doing this CGIS loop over logical specs. We have a logical specification which has it's this kind of universal quantified for all x phi of x and f of x type of thing. We use a CGIS loop, so we actually operate over this thing. tool that we focus on is this synthesizer, where it synthesizes basically, you take the logical spec and then you restrict it onto specific input-output examples. So the way you do this is, I mean, we have some sort of base case of like generate the simple program and then get a counter example with the verifier. And then you say, okay, if you have a verifier, it'll say your prior examples were wrong on input, let's say 0. I need you to generate a f such that f satisfies phi on input 0. And that's what we call a ground formula, which is kind of this predicate over atoms. It's like a Boolean formula over atoms, where the atoms are kind of predicates over the outputs for individual inputs. So the ground formula goes to the synthesizer will generate it all, we'll get a candidate function, send it back to the verifier, and we'll say, hey, great, you did great on 0, but actually 2 is wrong. And so we'll send 2 back over to the synthesizer, it'll generate for 2, and then it'll send it back to the verifier, and it'll eventually go until the verifier says, okay, actually the thing that you generated, it's not just right on these inputs that you provided me, but it's actually right on every input. And this is a relatively common approach, so this isn't like novel or crazy. This is another bit of details about how we're doing a novel approach that is not novel, that's relatively standard, but I want to mention in the way we synthesize in this, I guess in this synthesizer right here, this bold synthesizer, not the full logical spec, but the one but over ground formula, the way you do it is you take in the specification, you'll say, okay, can I synthesize anything of size 7 or less? And then it'll say yes, and then it'll return it, or it'll say no, and then it'll say, okay, cool, we failed on that. Now let's try it again on input, or is there any programs that satisfy it with size 8 or less, 9 or less, 10 or less? And you continue iteratively increasing the size. So this kind of biases towards small programs. And then eventually when you find one at some depth, it'll return it. So I'm going to go through an extended example on ground formula, and it's also over a finite depth, but I'm not going to be really talking about the finite depth. And for the ground formula, I'm just going to go for the simplest ground formula, which is input-output examples. So in this input-output example is that I'm synthesizing the del function, where I delete 0 from 1, 0, 0, that will return 1, 0, or I'm deleting 1 from singleton 2, which returns singleton 2. So here's our generated program, and here's our output. We're going to do kind of this bottom-up search. I'm going to go into the specifics of the bottom-up search later, but let's just say right now we're just kind of generating bigger and bigger programs. So let's say I'm trying to delete x from L, and I just say, okay, the del function is just the constant function that returns empty list. The output will return the empty list on both of these inputs, as expected. Cool. Let's start building some more complex ones. So maybe I project out the first argument, and that does exactly what you'd expect. It projects 0 or it projects 1. I can project the second argument, so it projects 1, 0, 0, or it projects singleton 2. Now let's do something a little bit more interesting. Let's extract the tail, so it should return 0, 0 for the first, and then just empty list for the second. And now let's do recursion. So note, if you remember our prior example, this del of x and the tail of the list, this was actually used in the overall program. So this is going to be something that should be present. So it's good that we are looking at this in the search space. This will be necessary. And we say, what is the output? And we say, I have no idea. The main reason we have no idea is that when you try to extract the tail of the list, or if you're doing a recursive call, the way it operates is you call the del, and then you go up to the very top of the function, and then you continue. The issue is that we haven't generated the top of the function. Remember, this is just going to be used as part of a overall function eventually, but right now there is no function. You know, we just say, oh, this is one subcomponent of the final program, and the final program will generate later. But to generate that final program later, we need to actually get the output here. So we have this kind of conflict where the del needs the full program, but to be generated to evaluate it, but to generate the full program, we need to evaluate this subexpression. So what do? And this is a very key difficulty here. So we can't evaluate a recursive call unless we know the full function. but that's only if we are using standard semantics. So our approach is to not use standard semantics. So we ask, okay, what can we return? We've got del blah, blah, blah. Well, we know that essentially the idea is we can return anything that's consistent with the specification. So we know that this is something consistent with the spec. If I return, sorry. Okay, I'm good. If I return singleton 0 for deleting 0 from 0, 0, then I get that singleton 0. If I delete 1 from the empty list, obviously I just returned the empty list. The specification doesn't talk at all about these inputs, so we're fine. So we say, okay, that's consistent with the spec, so we can return it. Although we do kind of have a bit of okay, we do have something more that we have to satisfy. It's saying, provided that, if you do delete 0 from 0, 0, we delete singleton 0, and then delete 1 from empty list, we get empty list. So essentially what we're doing is we are saying, yeah, we can synthesize it, but we now have kind of an obligation that we have to handle later. So I want to briefly go over the syntax of our language. It's a relatively simple, straightforward language. We're talking about specifically focusing on programs that have an outermost recursive call. We're not going to handle kind of nested recursion right now. We have a single variable x, or we have variables x, yada, yada, yada. And then we can do the standard kind of simply typed lambda calculus operations. So we can return unit, we can do, we can build up pairs like this, and then we can extract subcomponents of the pairs. We can do disjunctions, so we can do first and second. One difference is that we can do in left and in right. First and second is for extracting out products. One thing that we do slightly different is that we don't use matches. This is kind of due to technical reasons, but essentially when you are building these programs bottom up, you don't know what variables have been introduced in matches. So we don't want to have kind of a variable number of variables. So we're just saying, okay, we're using a fixed number of variables. So if we instead we want to be able to extract like the subcomponent of a sum type, we just use unleft and unright, and that will, unright of in-right of E returns E, and unright of maybe in left of E just gets stuck. And then we also have switches to be able to make it so that you actually do have control flow over there. And then our values are units, pairs, and then sums. So let's go into the semantics. The semantics are relatively standard. The only ones I guess I should say is that if E and we're using big step semantics because we don't need to use small steps. If E evaluates to in left of V, then if we unleft that E, then we just get that V. So that's kind of the only interesting one. These switches kind of do exactly what you'd expect, which is if you switch on this E3, you've got this, you follow the in left branch and then you return whatever it returns. And then we have a little bit of funkiness to handle recursion because we don't have lambdas in this core calculus. So even though we do in the actual problem, but we just kind of combine application and we combine application and recursion kind of at once, just to make things a little bit simpler because we've got this slightly more restrictive language. Now let's talk about, and so that was standard execution. Let's talk about angelic execution. In these standard semantics, we have these big step semantics. We parameterize by our specification fee. And this specification fee is used for these recursive calls. And it's useful to note that this angelic evaluation, it's basically the exact same as the standard semantics, except for how we handle recursion, in that we don't do this kind of recursive thing where we add the rec in and then add it to the bottom. Rather, all we do is we check consistency with the specification. So I'm not going to go through the details, but you can just convince yourself that everything here kind of looks the same. The one difference is right here, where let's say I've got f of v. Oh, note, by the way, I don't actually replace this f by anything. I just have the f kind of sitting there in the middle of nowhere. And then we use that as a key that, oh, we're doing an angelic recursion, which is where we return anything consistent with the spec by saying, okay, is fv, well, I can actually go into, I have a slide that works through this one. So let me actually do that. I've got f of v, and I evaluate under phi to what? We're using call by name, or sorry, call by value. So we say, okay, well, we obviously just have to evaluate e to some value v. So what we're actually asking when we're saying what is f of e, we're saying what is f of v. And we're saying, okay, it can return any v prime such that if we conjoin it with our specification, then it's satisfiable. So in other words, we're checking, is f of v equal v prime consistent with the spec? And if it is, then we can return that v prime. This kind of might fit in with some of your prior notions of angelic, which is talking about, is there any way in which kind of the program could satisfy the specification or like act correctly? And in this one, yes, there is. The one kind of funkiness here is that in the context of this angelic work, I guess the one kind of disconnect is that usually the angelic stuff is used for kind of ors. You know, you can take left branch or right branch non-deterministically. Right here, we just kind of say we're porting kind of the same style and feel of, is there any possible thing that can work, that would work out? But it's, you know, obviously in a very different context of recursion, and this is novel. So I want to compare this to some prior works like Smith and Sinquid. Our work is really nice because it is able to handle these with one rule. We're kind of able to handle everything. These, however, these top-down synthesizers have a lot of domain-specific reasoning that they have to do. So like Smith and Sinquid, they use not just evaluation, but they also have these rules for what's called unevaluation. They have rules for halting, resumption, subtyping, strengthening, all this complex stuff, whereas Burst is really nice because it has just this one rule that handles kind of everything. And besides that, your standard semantics can just stay basically the same. So I'm going to go through and kind of build up this algorithm piece by piece. We're going to start with the simplest possible thing. It'll kind of go wrong, and then we're going to see how can we update it to work a little bit better. So yeah, we're asking, okay, what can we return? If I've got the specification of these input-output examples, I generated this program, and it could return this, provided that we've got this del of 0 from 0, 0, return 0, yada, yada, yada. But that's not the only thing that is actually consistent with the spec, because this 0, 0, 0, and 1, 0 is actually completely unspecified. So actually we could return, we could swap the returns. We could even say, you know what? I don't care about the 4 returns. I care just about, or I can actually solve the entire task right now. I can just say that the recursive call returns what we want and then be done with it. This obviously doesn't actually satisfy the specification, but it does angelically satisfy the spec. And so which of these is the right one? Well, I want to formalize what angelic satisfaction of the spec is. So we had this prior notion that we went in, which said that it satisfies using standard semantics. So using standard semantics, it evaluates true. In this one, we're talking about the same thing, but under the angelic semantics. And we have a theorem relating the two. So namely, if you satisfy using standard semantics, that means you also satisfy using angelic semantics. So that means that we are complete. We do generate in this bottom-up procedure everything that does satisfy. But unfortunately, we have a non-theorem, namely that if we angelically satisfy, that does not necessarily imply that we standard satisfy. And that means that this algorithm is not sound. We're not necessarily always going to be able to generate the correct program. We might be generating spurious programs. So I'm just going to give a quick recap. We want to synthesize these programs bottom up. To do that, you have to evaluate these sub-problems, but you can't use standard semantics for that, but you can use angelic semantics. So we synthesize the sub-programs using angelic satisfaction. and that's using FTA synthesis, which I'll talk about later. Angelic satisfaction over approximate standard satisfaction. So some of the programs are spurious, so we have to figure out which ones are not spurious. So we add in something to our algorithm. Essentially, we have this function called getAssumptions, which essentially inspects those provided obligations that we generated before. And if there are none, then that means that the function f satisfies immediately, so we can just return it. But if there are some assumptions, then we can extract those assumptions as psi and then reintegrate them with our original spec. So let's go through actually this extended example. I'm synthesizing del. I angelically synthesize this program. This program is obviously incorrect because it just returns empty list on everything, but it does angelically satisfy using the ideas that if I delete 0 from 0, 0, it returns 1, 0, and if I delete 1 from empty list, it returns singleton 2. Then so I say, okay, let me strengthen my spec so that I will now satisfy this, and we get a failure because at this layer, remember I said I'm doing iterative deepening, essentially. At this layer, there is no programs that satisfy. So I have an issue. And the issue is that I made an incorrect assumption. So I need to be able to handle when I make incorrect assumptions. And the way you can identify that is with failures of angelic synthesis. If the angelic synthesis fails, we know we made a bad assumption, so we backtrack on the assumptions. But if it succeeds, then we continue looking at the assumptions until we eventually terminate. Or we need to backtrack. Once we add this, then we are a complete procedure. And this is very inspired from so in this work, this is kind of similar to like DPLL, where we're doing this backtracking search where we go down a path and then we find some sort of conflict and then we go, uh-oh, we made a bad choice and we need to backtrack. So, you can look at this, you do this synthesize angelic. If you fail, then you say, uh-oh, and you backtrack. And then if you succeed, then if it actually satisfies, you return it. Otherwise, what you do is you will look at the new assumptions that you've made, you conjoin them on. If that fails, then you're implicitly backtracking on that failure until the failure propagates up here. And then you go down the other path, basically, and you negate that omega. But we have an optimization from, DPLL went to CDCL by adding in this kind of, God, I forgot what they call it in CDCL, but this unsat core, which basically which allows them, when they do this backtracking, to backtrack on more general predicates. And in this context, essentially the way we do something similar is we get the unsat core you could think of in the failure. And that's and then we add this to this global omega, which serves as an anti-specification. So basically we then, we negate everything in that unsat core on all future synthesis calls, which can be really helpful. So let's go back to this extended example. We've done this whole synthesis. We've hit a issue where we need to backtrack. So we do backtrack, and then we, as I said, we negate the omega right here. So we add in a negation of this, and that will ensure that we don't pop this same program again. So we pop a new program. This program looks really good, but there's no specification on empty list, so it's going to potentially return something stupid like singleton 0. But fortunately, we're not in trouble, because when we check out the specification, when we check out the assumptions, we actually get a great assumption, which is deleting 1 from empty list returns empty list. We use this, we make a new angelic call, and we actually get the desired program, such that when we inspect the assumptions, we get nothing. And then we're done. So I just want to go through one more time what we're actually doing here. And I'm also muting my phone. Oh my gosh. I apparently failed at muting my phone. I'm sorry. There we go. We take in a specification phi. We do an angelic call. That gives us a candidate function f on success. We inspect the assumptions there. The assumptions, if they're nothing, then we're just done. If there are some assumptions, we have to go here. And then sometimes those assumptions are spurious, so we have to do this kind of backtrack as well. We have some theoretical, actually I should check the time. We have some theoretical guarantees on this work. Namely, we have soundness. So if we return a program, that program will be correct, and we have completeness. So if there's a satisfying program, we will return such a program. And what's nice is that kind of prior work either had to settle, in terms of completeness, they had to settle for kind of like relative completeness, or they just didn't even have completeness, namely because of how complex reasoning about recursion is. It's just tough. So fortunately for us, because we don't really enforce that reasoning in the same way, we don't have to do the same type of. It's easier for us to be complete. So we evaluated on the Smith and Myth benchmark suite, which is classically just an input-output example-based benchmark suite, but we added in synthesizing from reference implementations and logical specs. We evaluated with a 2-minute timeout, and we found that we performed as well as or better than prior work on this benchmark suite. Compared to Smith, which tackles I/O examples, we performed basically comparably. But on reference specs and logical specs, we found that we were able to outperform them prior work, which is great. So we did an ablation, namely we have this specification strengthening. So you might ask, is this necessary? Can you just use Angelic synthesis? And you kind of can, actually. It does handle some of the easier benchmarks, but some of the really tough ones, it doesn't work as well on. And you do need this specification strengthening loop to kind of get more of a high percent. So now that was kind of the overall picture. I'm going to go into a little bit of the details of how we do this bottom-up synthesis. We're using, as I mentioned earlier, this thing called FTA synthesis. So it's FTAs or finite tree automata. They're automatas. They can be thought of as an extension to DFAs. So DFAs express languages over strings. FTAs represent languages over trees. And so the main idea or insight is that programs are also actually trees. So you can use these FTAs to describe what are valid programs. So essentially you want to build this automata such that the automata accepts all of these, such that everything accepted by the automata satisfies the program, or in our case, angelically satisfies the spec. So here's one of these FTAs for example, the input-output example 1 goes to 9. You have this 1, you know, okay, that's the input, and then you can perform a variety of optimizations or operations on that, and then eventually you can get to the actual final value, which is 9. And notice that all these other states are not accepting states. That's because if you ever get to a case where you're returning something like 6, that's not correct. You don't want to return 6, you want to return 9, so you want to not accept something that ends in 6, but you want to accept something that ends in 9. And so we have a guarantee such that this should be a star. If you have this is an input-output example. If you have an input-output example of E maps to E prime, then you have some function F is in that automata that is built from this input-output example. That F is in the input-output example if and only if the function kind of angelically evaluates to E prime. So here's a formal definition. You can see this kind of looks like essentially DFAs, where you've got states, you've got final states, and you've got transitions. The only real difference is that these transitions are not like some sort of del on a single queue goes to another single queue, but rather the transitions can take in multiple arguments. So for example, right here, are these all single transitions? Yeah, they are. Well, this is because this is all fixed multiplications, but you can do something where you can imagine plus is a binary operation. So you want to be able to have plus takes in 2 states and returns a new state. So I'm going to do an example building an FTA for this input-output example. Specifically this one, I'm going to ignore this one. So in this one, what is x? X goes to 0 because I've got x0 right there. And the L is the list 100. So sorry, I should mention In this style of building up algorithms, essentially the states are values. So if I just had the return value of 0, then I would return 0. So the idea is that if you ever stopped, if you had a accepting tree that ended at this value, that would be what the value returns. And then you want to make your final states the values such that they satisfy the spec. And then in that way, if you ever build up to a final state, you know, because the final state is a value that satisfies the spec, then you're returning a satisfying value. So now let's build up. I've got this list, it can return this. The head of that is 1, so that means if I have the program head of L, that would be just the return value 1. I can also extract the tail of L, so it gets 0, 0. I can actually extract the head of 0, 0, and it gets to 0. So in this way, I'm kind of modding out by equivalent ones, because now anything that I build up from 0, I'm also building up from the tail of the head of the L. So in this way, kind of, we're saying, okay, if you ever get to this value, it doesn't really matter the path. And then 0, I can talk about, oh, the successor of 0 is 1, and the predecessor of 1 is 0. So you've got this loop. So x is equivalent to successor or predecessor of successor of predecessor of x, and you can continue going along this loop as much as you want. If you've got the 0, 0, you have the tail of it is the empty list. Now here's a binary transition. Del is a recursive call. I'm calling del on 0, 0, and 0, and it can return singleton 0. This is where I'm doing now an angelic evaluation. So I'm angelically evaluating one instance of deling 0 from 0, 0. It returns the singleton 0. I can do this append, which is another operation, and it can return 1, 0. And, you know, I don't know if, I think I didn't put it in here, but I can, because I'm doing an angelic evaluation, there isn't necessarily this single del. I can have actually multiple dels. Oh, here we go. I did do that. So I had a del where I can do del of 0 and 0, 0. That can just return 1, 0 because that is a valid call, at least with this specification. So this builds up an FTA that talks about any valid program. All of the valid programs are those that end right here. So if it ends here, then that means that the program is accepting on the input values of 0 and 1, 0, 0. God, that's a lot. Okay, so let me just go through quick. I want to summarize. Essentially, you can do this for all the atoms, and then you can do some work to combine the things, and I guess I'll go into that later, that combines this FTA with this FTA such that it merges the accepting programs. So here's kind of our methods of building up the programs. We're building up what is in queue, what is in the transitions, and what is in the final states. I guess there's not too much necessarily to go into in here. Notice that we have this angelic recursion, and it kind of matches your intuition. All of these rules should look very similar to the rules that you had in, or to the rules that I showed about just standard, or I guess angelic semantics. The one difference is that now we have this, you know, Q sub V and all that stuff. And then there's one other thing that I want to talk about, which is switches. So on switches, when we're evaluating, we only evaluate the side that kind of actually is productive. So that actually kind of finishes. But if we have this, but what about the branch that isn't taken? On the branch that isn't taken, it doesn't matter what we write in. It can be anything. It can be buggy. It can be whatever. We can just have it error out. So we have this default sentinel state bottom, and then bottom is always in there. And essentially for every single language in our, or for every transition in our language, we add a transition that just lets bottom do whatever. But the only way bottom can actually result in final programs is by being combined in switches. So bottom is not final. But it just is a way of expressing essentially accept everything as a state, and that is what fills in the non-taken branch. And we've proven some theorems. So like if a program is in the language of this constructed automata, then that means that language angelically satisfies the specification V. So yeah, let's talk about this example FTA building. I get this A1 from building it up for there. I also build one up for 1 singleton 2 that builds A2. We want something that satisfies both of them, which means that it corresponds to programs in both languages. So you can extract that by intersecting these FTAs. So any program in the language of the intersection also satisfies both of the specifications. I'm not going to go through this because I don't have enough time. We have this algorithm that essentially does this. It's from a very, very high level. What we do is we turn our specification into DNF form, and then we try each of the individual, I guess, clauses in that DNF form and say, okay, let's and everything in this clause, does it synthesize anything? Let's and everything in this clause, does it synthesize anything? Yada, yada, yada. I'm going to go into some of the low-level details. So we ensure termination of our programs. This uses some default metric. It has to be a well-founded metric, and we basically say, okay, if you have this well-founded metric, then we know what recursive calls are valid, and we know that we can't have like an infinite chain of recursive calls. So in this way, I guess we're not tackling programs that are, Turing complete. We're only generating guaranteed terminating programs. And we also just have this default metric of the size of the input. We also do a finiteization of width. So I talked a little bit about how we do finite depth, where you synthesize only to a finite depth, so you don't kind of iteratively continue building up whatever. But we have this recursive call f of v equals v prime, where we can return anything consistent with the spec. This is like anything. So, it's pretty hard to talk about, well, we can just return anything. This allows for infinite width of transitions because you can transition to anything. Fortunately, we can actually kind of bootstrap ourselves using finite depth. So because we're doing a finite depth program, when we make this recursive call, we can build up an FTA for that smaller input. We check out what are the outputs that can, in that finite depth, be satisfied. And then we use those and reintegrate them into the, we use those as the possible outputs. Because, if I'm talking about programs up to depth 5, and then there's a program at depth 6 that can return, 100, it doesn't matter, because at this kind of bound, at the bound size of 5, we're not going to be able to generate that. We also have an optimality condition. This I'm not going to go into, but remember how I talked about how in our original algorithm, we had this backtracking search. The issue is that we can maybe generate some program that is suboptimal. It returns something that's maybe not the smallest possible program or something like that, and that's undesirable. So we do have a way of generating something that we guarantee to be optimal. Namely, rather than say, oh, let me traverse left and then traverse right, we traverse both at the same time. We add them both kind of into a priority queue where cost, or I guess goodness or whatever, priority is aligned with how good, the priority is aligned with how good the program is. And so we generate the best programs first. And, with a little bit of reasoning, you can ensure that this does in fact return the optimal program. We also did some optimizations on FTA construction, and this corresponds essentially to normalizing the actual terms, because even though FTAs do normalization themselves, having fewer programs in your space makes intersections faster. So we essentially were able to just look at prior work and see what did they do and integrate that into our thing. So we essentially only permit switches or branching at the outermost level. And then we also, for those of you who know about introduction and elimination forms, you can prove some things talking about normal forms where you don't have introduction forms and then immediately eliminate it. So we essentially, so this is kind of taken from Myth. This is the Myth paper. They have these separation into intro and elimination forms. And so what we do is we generate essentially the same thing. We generate only valid intro and elimination forms. And we also do what is it? We also actually ensure the correct, or was it the correctness? Sorry, let me just think. We also we also ensure well-typedness. So essentially what we do is we take our language, we separate it into some of the types so that we ensure that we only generate well-typed programs. And then we also, in addition to kind of having these types on our classes of nodes in our FTA, we also have, is it an intro or elimination form? And we only generate kind of according to these rules. We also kind of improved the CGIS loop. So we have this, oh, I should have mentioned our verifier, for practical reasons, we just use a fuzzer. Like, I know there is some work that can verify recursive functional programs, but it's not as, it requires kind of basing in some side of form of underlying theory. We don't want to do that, so we're just using a fuzzer. So we take in this logical spec, we have this whole thing. What we would really like to do is actually make it such that when we generate candidate functions, it's not just any candidate function. So let's say we have a specification talking about 0, 0 in our ground formula, but maybe our verifier or our actual original logical spec has some form of discussion of like singleton 0, so that when I make a recursive call to singleton 0, if I only looked at the ground formula, I could return anything, but actually I can just go back, not just look at the ground formula, but look at this logical spec. So and then say, oh, even if according to our ground formula, we can return anything, I know that anything that returns like 0 would eventually be wrong. So let me integrate the logical spec with the ground formula. We also want to handle these arbitrary predicates. I mentioned this briefly. We turn it to DNF first because it's kind of bad to use unions and then intersect. You kind of get a bit of an exponential blow up. And then so we've got these conjuncts and disjuncts. And rather than treat it as a whole program where we do these unions, we rather just search through each individual clause in this DNF. And then each conjunct within the clause is just used FTA intersection. There's some related work. There's a lot in recursive functional or program synthesis, but there's also actually some work in using angelic synthesis, but that's primarily in the context, or it doesn't use angelic recursion, and it's primarily in the context of repair. There's also some future work, which I really should not go into because we don't really have the time. I guess I'll very, very briefly mention it. I've done some work talking about kind of like how can you verify full data structures. You could talk about, oh, is correctness using a test suite? It isn't really, it has all these issues. So the better thing to do is to use a relational spec, which relates the various problems to each other. This solves kind of some of these issues. And it's nice because it doesn't talk about the individual implementation, but it talks about what is a set in general. Now you could say, oh, this is actually a hugely exciting thing in the context of synthesis, because this is something that you need to be correct. I would like to maybe be able to generate all these programs at once such that they satisfy this specification. That would be really, really useful. The issue is that when you do this, let me think of the right way to say this. The issue is that these types of specifications, they are not the logical specifications that we said that we were able to handle before. So what can we do? Well, basically, we're changing our synthesis tasks so that it can handle these more general predicates, but then that caused some scaling issues. So we're doing some fancy FTA stuff using alternating finite tree automata actually to generate. So yeah, I think that's it. I'm happy to take any questions. Thank you. And let me see, how can I stop presenting? There we
go. Thank you. I see Kirill has raised the hand, so you can ask your question.
I have actually some questions. How do you track the semantics of small parts? I have seen no types on them. And
the semantics on what?
The semantics of delete and some other like embedded functions. I've seen that the device knows that deletes the first element and leaves the rest of the list intact. How do you track it?
How do we try it?
How does
tracking.
it?
Oh,
Yes.
So let me. I should have just not stopped sharing my screen. Sorry. I'm just going to share my screen again. Yeah. Okay. I am presenting my screen. I believe you can see this. So I should have built an animation for this. Sorry. But essentially it tracks via looking at how you actually get the final result. So when we talk about, we find some program that lies in this language, that program corresponds to a concrete actual run. So it's going to be some sort of tree that ends here. So let's actually build one up right now. Maybe it'll go there. And then it's del as the call. And then I guess it's that and then tail. So this is the actual tree that is accepted. Is this tree corresponds to the program, take the head of the list and append it onto a recursive call using the tail of the list and X. Look right, this tree and how it corresponds to the accepting run in the automata actually encodes what the assumptions are made. Namely, I go del on 0, 0, and 0, return singleton 0. So that means that from this specific run, I'd actually get the assumptions that del of 0, 0, 0 equals singleton 0. And so right when we do this extraction of the program, we also get all the assumptions that were made. Does that make sense?
Yes, that makes sense. The next question is, aren't the results overfit on the examples?
Great question. Okay, so this is a great question, and I'm going to also say it's kind of almost a philosophical one. It is underfit in some ways, in that we return the program that is most general, or sorry, most general is the wrong term. We use the approach of Occam's razor principle, which is if you have the simplest explanation is probably the right one. Simplest in this context is smallest number of AST nodes. And that works kind of well, but it also has some kind of silly behavior like this, where I say, oh, the length of the list should be less than, or the length of the output should be less than the length of the input list. And it just returns empty list. And this is like fine, it's the simplest example, but it's unsatisfying because it, like, obviously, if I'm giving this specification, I'm not talking about with this name, I'm not talking about returning the empty list. So in that way, I guess it isn't, what I would like is for it to be more aware of kind of using some intuition behind why would I be providing these examples in this sort of way. And so I'm personally interested in using kind of essentially codex to help bias our search a little bit more towards slightly more likely programs rather than just simplest explanation is the best. So I guess, sorry, that was a bit of a rambling response, but from a very, very high level, we don't overfit because overfit outputs are very long usually because you have to do all these matching. But even what we're doing is still unsatisfying. Like, it's standard in the literature, but it's also, to me, you can do better. And I want to do better.
Okay, so the next question is, how do you limit constants? Because each constant in the resulting code is
great question.
Point of freedom.
It's a bit of a
degree of freedom.
I'm not going to call it a hack because that's too disparaging on myself. I'd say it's a unique approach, maybe. Essentially, we're maybe it's a bit of a hack. Essentially, what we're doing is we are we're working only over this very, very where is it? We're working over this very limited language of basically just algebraic data types. Our encoding, because we work over ints, or I guess nats more specifically, our encoding is the stupid encoding. Our encoding is just
0 and +1?
0 and +1, exactly.
So therefore lower numbers are preferred because they are structured.
Yes, exactly. So if I want to talk about 100, I have to talk about 100 AST nodes, which is fine, but it is limiting. It's absolutely limiting because 100 is if you do want to have special cases that do use large constants, it's hopeless to satisfy.
Okay, what kinds of programs do you plan to generate? Business logic or data structures and algorithms?
In this work, data structures. God, I would love to do business logic. I think so. Business logic is kind of like where I think is the right place to be focusing on long term in synthesis, because I also think that business logic has kind of almost like very simple forms in a way. Like it's often about gluing and things like that. And it's like gluing things as well as doing validation checks. And this is actually, I would say, something that is it is more often used than these data structure manipulation tasks. And in some ways, it's also easier than data structure manipulation tasks. But I think that the difficulty of doing business logic is using business logic often has kind of like, basically, my thought is you can't really do it well when you're working statelessly. I wish you could, but it seems in my experience that you can't really. So I think that one thing that you need to talk about is how do I appropriately encode kind of state and also like kind of lots of dependencies that go everywhere in the code. But I think that if you can talk about that and you can perform a good form of specification, this type of work actually I think would be really great for it, because this type of work works really great on this kind of not very large pieces of code. That's kind of this approach, and I'd say most approaches right now. The issue with scaling is with not, or I guess specifically with this, the scaling is not with the specification, which is great. The scaling is purely with the size of the program generated. So if your program, maybe even if it's long, but there's a special DSL for expressing it, or it comes in some specific form, this type of work would be great because all this complexity of the underlying assumptions of your business logic, you can write in the specification. We handle, and we do not scale poorly with having large specifications. We scale poorly with complex problems. So if you're able to encode the business logic, I do think that this is a good approach, or the general approach of like bottom-up synthesis would work well because of its unreliance on specification insight.
I'm out of questions. Thank you for answers.
Yeah.
Does anyone else have any questions? I've just heard someone trying to ask a question. Dmitry?
It was me, yes. Andrews, thank you for a very excellent talk. It was rather understandable comparatively to everything that happens usually here. I have a question. Does your approach have difficulties when you don't have some ground-based examples for program that should be synthesized? For example, when specification is for every you need a program that computes to itself, like
yes, yes.
And also, how consistent is your approach if you try to change the language in which programs should be synthesized? Will something drastically change if you add the scheme symbols, scheme quotes, unquotes, and stuff like that?
Okay.
Thank you.
2 questions, both of which are great. So the first question was about, when you're doing this, I'm pulling up this ablation for a reason.
Basically, I asked, can you synthesize quines and program
Yes,
that,
yeah. Can I generate? So I would say that, like, in terms of how well we do with very loose specifications, we're fine in the context of being able to find a final satisfying program. The issue is where we generate the recursive calls. That if you have a recursive call that performs, that is unconstrained, that is highly unconstrained, there is, we scale badly with it. And it's kind of a propagating poor application. And actually you can see kind of we fail on like the function nat max, which is find the max of two elements. And because the specification that we gave for that nat max is something like, oh, the max of 4 and 4 is 4. With that specification, you can make a recursive call to 3, 4. You can make a recursive call to 4, 3. You can make a recursive call to 3, 3, 2, 3, yada, yada, yada. Things like that. It's very, very broad in what you can make a recursive call to. So that recursive call is unconstrained in what it itself calls, which is unconstrained in what it itself calls. So what you get is you kind of get this like almost iteratively worse and worse result where, 0, 0 maybe can return something like 0, 1, and 2. 0, 1 can return 0, 1, 0 through 5, and 1, 0 can return 0 through 5. 1, 1 can return 0 through 10. And you get up to the point where when you're at 4, 4, you can return any of like, 5,000 different outputs. And then when I actually finally do the intersection, I have the FTA intersection becomes just basically impossible. So this is something that we do badly at, where it is really tough to handle when we have bad or very unconstrained recursive calls. This is why the input-output example, so this burst prime, where we don't perform specification strengthening, is even worse at it. And that's why this input-output example performs so badly on those examples, because when it has such unconstrained aspects, because it'll just give like one example of like 0 on some very large input and say, this is a large enough input that you should be able to figure out the recursion, and it's actually quite difficult. So I would say that what we need to do is we need to be able to the way that we're thinking that we can solve this is by using this approach called SynGAR, which was program synthesis using abstraction refinement. And essentially what you do is, rather than build up all of these concrete values in your FTA, you rather use abstract predicates to discuss large sets of values. And then once you get spurious programs using those abstract predicates, you can refine them. Yeah. So I'd say that the main difficulty lies in this this exploding search space. Without some sort of thing constraining recursive calls, especially if you make a lot of them, it gets worse and worse. So you do need to have some sort of if I was to build a full, fully powered version of this, I would absolutely need to use abstraction refinement in some way to tame the search space such that it has better scaling on these unconstrained recursion. You had a second question.
Well, basically the first question was, could you synthesize something like quines for programs?
I'd say probably
itself. Probably not. Yes.
Yeah, that would be my expectation.
Did you try to somehow change the language in which synthesize programs?
Yes. Yeah. Great question. So we are. Yes. I guess to answer your question, it is dependent on the language slightly. So we didn't change the underlying language, but what we did change is we changed what functions were in the context. We just kind of were playing around with it. Eventually, in our final benchmarks, we used the default, the exact same context that were present in prior work, but we investigated how badly we perform when you add in more language features, more functions into your context. And we were expecting that we would do significantly better than prior work, which is super poorly affected by adding in new language features, new combinators, things like that. We did outperform the prior work. We were less impacted by having these new things because prior bottom up or top down things, essentially it just has more choice points. Whereas, yeah, we have the choice points, sure, but they all kind of fit into the FTA nicely. But it wasn't as well as we expected. And the main reason was basically just FTA intersection. When you have more functions that can combine the nodes, it just slows down intersection. And that's the main reason that it does have an impact where we were hoping it would have negligible impact. It had substantial, even though it was better than prior work, it did still have substantial impact on how we performed. And which is a shame. In terms of how we could handle that, I mean, I want to believe that I don't want to just use, here's the one solution and then it solves everything. But most of these scaling issues, especially with size of the FTAs or complexity of intersection, these are the types of problems solved by doing abstraction refinement. So we're hoping abstraction refinement can solve those. Although that's actually not what I'm primarily working on, even though it would work with scaling a lot. Rather, I'm trying to tackle the problem of making, of making these failures be much larger so that when we can do these anti-specifications, I guess making these failures have larger things so the anti-specification gets bigger, and also when we get the success with the kind of provided sentence, we want that provided sentence, that witness, to be much more general. And that's kind of what I'm focusing on now. But I do think that, sorry, I rambled again. To answer your question, yes, absolutely it has an impact. It's less than other things, and I think there are ways of solving it, or at least making it even less impactful than it is right now.
Okay, thanks.
Yeah.
Does anyone else have any questions? All right, I think we can end this now. Thank you, Anders, for your talk. It was really insightful.
Thank you. Thank you for the great questions also. This was fun.
Thank you.
Okay.
All right. Have a nice day.
Bye-bye.
Bye-bye.